Welcome to Radioactive. Oh, here it comes. Radioactive. Yeah, nice little transition to some nuclear chemistry, part 2. All right, so we were talking about what it means to be radioactive, what it means to be unstable and decay, and all those terms. If you don't remember some of those terms, might be a good idea to pause this, go back, take a look at all those terms. What does it mean, unstable? What is decay? That kind of stuff. So if you look at the word transmutation, this means changing. So we are starting to change things. Now, back in the early days of the chemical alchemists, the kind of like mystical, magical pre-science, like the wizards, they thought that you could change one element into another. So, for example, you could get gold from boiling down your urine, which is clearly not true, kind of gross. But we have since discovered that it is true during nuclear chemical changes. So the word transmutation is a history of being like almost blasphemous. When Ernest Rutherford and Alfred Soddy were discovering the nucleus, when Rutherford mentioned the word transmutation, it was like, shh, don't say that, it's crazy, but it is actually true. What does it mean? It means we're converting an atom of one element to an atom of another. Now, how would you do that? How can you change the identity? You would be changing protons. But wait, you can't change protons. Well, the whole point that we've always said, don't touch the protons, is because it would change the identity. But now that's exactly what we're doing. So this can happen two different ways. It can happen naturally or artificially. So if you think about it, if it's natural, it's just gonna happen. It's gonna be spontaneous. So this is one radioactive isotope, one radioisotope breaking down all on its own. How can you tell it's breaking down all on its own? And sorry you can't see that. It says one reactant left of the reaction arrow. What are you talking about, reaction arrow? Well, stay tuned. We're going to talk about how to indicate that in this video. So natural transmutation is when the nucleus is breaking down all by itself. It's just like carbon-14. You should know from earth science and other classes that carbon-14 is a radioactive isotope. It's unstable. It's not going to need any help. It's not going to need to be bombarded by any particles. It's just going to break down, giving off. Now remember, what happens during decay? We give off energy and particles. We're going to talk about what kind of particles those are today also. Some things are going to transmutate or change, but they need a little bit of help. And so that's called artificial transmutation. Artificial transmutation, obviously not spontaneous. It's got to be coerced or induced to get it started. So the nucleus is bombarded or attacked with high energy particles to get it started. So we're talking about something that wouldn't necessarily break down by itself, and we're getting it started. So if you think about it, if we have the item that will break down and a particle that starts it, we have two reactants. So the nucleus being bombarded and the high energy particle. And again, sorry about this little thing here, but all these notes are available in the PowerPoint slides PDF. Okay, so we talked about how in decay we give off particles and we also give off energy. Can you please go to reference table O? Table O, it's on page 7. We're going to talk about some of these symbols, some of these particles and energies given off during decay. So the radiation particles emitted during the nucleus decay process. Let's back up a second. Are we familiar with the word emitted? That's a word that the Regents uses a lot. Emitted means given off. So particles that are spit out or given off during the breaking down or decay process. So when you think about radiation, you're thinking about, oh my gosh, I'm going to grow an extra arm, I'm going to turn green. No, but it is dangerous for us to be exposed to, because what it can do is it can get into our human body, changing the DNA of our cells, changing the way our bodies work. So that's why it's dangerous. So we have a couple different symbols, and we're on table O, page 7. You notice we have this symbol. Kind of looks like an A. which it is in the Greek alphabet. This is called alpha. And you should be familiar with alpha because of the gold foil experiment. Remember that? Gold foil experiment. That was Ernest Rutherford shooting a piece of very, very thin gold foil with these positively charged particles. So there's alpha. We have some other particles. Take a look. This is called beta. Notice its charge. It's right here. Beta is negative. Then we have this one. Kind of looks like a Y, but it's not. This is called gamma. Gamma is actually not a particle. This is pure energy. Because remember, there's matter and there's energy. Oh, okay. Well, I wasn't ready for you, but here we go. Then we have positron. Looks like beta, but it has a different sign. So these are 1, 2, 3 particles in the energy that could be given off by decaying nuclei. Reference table O. So let's talk about these. Can you go to reference table N, please? Flip it right over to page 6. Take a look. It shows you a whole bunch of selected radioisotopes. So again, these are radioactive. These are unstable. They want to break down. So if you notice under the column that says decay mode, so find an alpha. So maybe about a quarter to a third of the way down, I see francium 220. And remember, the 220 is the mass number. Francium 220. That means it's radioactive. It's going to decay. What is the particle that francium 220 is going to give off? It's an alpha. So let's back up. What is alpha? So let's go back to table O. Alpha. If you notice the notation for alpha, it says 4/2 He. That's helium. An alpha particle is just a helium nucleus. Be careful, not a helium atom, because an atom would also include electrons, and this is just the nucleus. So 2 protons, 2 neutrons. Alpha is the heaviest of the atomic particles that we're talking about here. So positive charge, think the gold foil, GFE. Mass of 4. How do I know it's mass of 4? Well, if it says this top number is the mass number. That should say 4. Sorry, hard to read. So alpha, back to table N. If you find uranium-238, this is the absolute last one on the chart. So you undergo alpha decay. Notice it says decay mode is alpha. So we can show what happens when uranium-238 gives off its alpha particle through what we call a decay equation or decay reaction. So here we have uranium-238. We added in the 92. Oh my gosh. Eraser. Let's clean that up. So what is this 92? You should remember that's protons. That's atomic number. Did I need to write 92 there? No, because it's indicated by U. Uranium is only going to have 92 protons. So you don't have to write it in. I do, and you'll figure out why in a moment, because it's going to help me with my math. So uranium-238 is going to spontaneously or naturally decay. What's it going to do? It's going to give off, of course, it's going to give off alpha particles. So we need to draw in an alpha particle. 4/2. You can either draw it like this with the alpha symbol, or you can draw it 4/2 He. They're both the same, synonyms. And if you are confused, it's on table O. Okay, so uranium-238 spits this out. But what does it become? Because I've lost 2 protons. 2 of the 92 protons are spit out in the form of alpha. What am I left with? Well, I'm left with 90 protons. My total mass to begin with was 238. 4 of that mass was spit out in the form of alpha. What am I left with? 234. Well, okay, great. What is going to be the symbol for the thing that I've transmutated into? Let's go to periodic table, because honestly, I don't know off the top of my head. You don't need to memorize periodic table. You can always look it up. So who is element 90? This is thorium, named after Thor. Remember that guy? Oh no. So now, the other thing that is always given off is energy. Now, you can write plus energy in your decay reaction, or you don't have to. It's up to you. But notice, we are following law of conservation. So if our total mass here on the left is 238, our total mass, 4 and 234, should also equal 238. If we had 92 protons to start with, we should have 92 protons to end. They are not part of our big particle anymore. They've been spit out in terms of the alpha, but we still have 92. So notice we're following law of conservation. Do we write a U here? No, we don't. We have transmutated into a brand new element. So this is kind of a generalization of everything that always happens in an alpha. We're always going to decrease our mass by 4 because 4 of that mass is gone with the alpha particle. Atomic number or number of protons always goes down by 2 because 2 of those protons are gone in the form of alpha. If you want to talk about neutrons, because of course they're in the nucleus too, we've lost 2 neutrons. So because the mass is 4 and 2 of that 4 is from protons, the other 2 must have been neutrons. Don't worry about this too much, like the nitty-gritty. The Regents would ask you something like, complete the decay equation or decay reaction for radium-226. Now be careful, there's radium and there's radon. Be careful, this is radium. So I don't know what radium is going to give off. Well, you might know because it's under the heading of alpha, but if I didn't know, I'm going to go back to table N. I'm going to see that radium-226 gives off alpha particles. So 4/2. I'm going to write it this way now. You can also write 4/2 alpha sign. That's fine. They are synonyms. Okay, so this is the particle that's been spat out. Now, what is it going to transmutate into? Follow law of conservation. 226 over here. 4 plus what is going to give us 226? How about 222? By the way, if I make a math mistake, I'm really sorry. I hope to not because it's embarrassing, but my calculator is somewhere. So notice we're still going to add up to 226. I have 88 protons. I need a total of 88 protons this side. So 2 of those protons have been lost to the alpha decay. The other 86 remain in our kind of remainder product. So do I write Ra right here? No, I don't, because I am no longer radium. I have transmutated into somebody else, and I'm going to look it up. Oh, there it is. Radon. Rn. You can write plus energy or not, up to you, because it's always given off. Alpha decay. Hope you're feeling good. If not, go back, watch it again, give it a try. Here's another kind of decay. It's called beta. So if you're looking on table O, again, beta, look at the notation. The upper left number is a 0. That means mass of 0. The lower number means -1. How can you have negative protons? Oh, if you're not a proton, you're actually an electron. That's another way of saying electron. Betas are electrons. So you should know electrons are negative, so that will help you. Now, on the old reference table, on table O, next to where it said beta particle, it also had in parentheses electron. So I recommend in your reference table, right next to where it says beta particle, parentheses, electron. Used to have that, they took it out, who knows why. Beta decay is another kind of decay. We're still going to have something that breaks down, but it's instead of giving off that alpha, it's going to give off beta, which means our product will look different. So if you want to look on table N, you can see about a little more than halfway down, you have phosphorus 32. Phosphorus 32 gives off beta decay. So if it gives off beta decay, we write beta symbol here. If you don't remember the beta symbol, table O. Now, what does it transmutate into? Let's follow the law of conservation. The total mass over here is 32. So my mass is also going to be 32 here because 32 plus 0 is 32. Now, this is the part that gets a little tricky for students because we're dealing with negatives. I need a total of 15 protons. I have -1. I have less than 0 now. How am I going to get to 15? Well, if I have 16 -1, this whole side of protons is now 15. Do I write a phosphorus here? No, I don't. I go to periodic table, and I see who is element 16. Oh, that's sulfur. Now, if you want to look, if you're on periodic table, notice that sulfur 32 is the most abundant isotope. It's what we have on the periodic table. This is stable now. The decay process is over. We're done. So this would not continue to decay. Sometimes they would, but this will not. So what happens in a beta decay? If you notice, let's take a look. Okay, so mass doesn't change. Protons up by 1. No change to mass. Protons up by 1. Okay, so think about it. If the mass doesn't change, but you gained a proton, we must have lost a neutron. Okay, let's try another one. So technetium-99. If I didn't know it was beta, I would take a look on table N and see that it is beta. So let's write a beta symbol. Now you can write it 0 over -1b with the tail, or 0 over -1e like electron. What is it going to transmutate or change into? Let's take a look. Mass is 99 here. How am I going to get a total mass of 99? Well, there's nothing from this. Mass remains. 43 protons. How do I have a total number of protons 43? Well, something -1. 44. 44 -1 gives me 43 total protons. 43. So do I have technetium over here? No, I don't. Go to periodic table because I don't know. Ru. I believe that's ruthenium. So that's a beta decay. Did we change our nucleus? Yes, we did. We have changed from one element to another. It's called a transmutation. Now, earlier we talked about natural and artificial transmutation. Notice how this, all by itself, is going to break down. This is a natural transmutation. Gotta love this pen. Okay, back to table O. Notice gamma is radiation. Gamma has no mass, no charge, because it is not mass. It is energy itself. It is high energy photons. If you're concerned, I don't know what a photon is. You're going to talk about it in physics if you take it, which you should. But it's just high energy. This is not an actual tangible particle. It's extremely powerful. It's going to get through. It's going to come get you. So here's a diagram. So let's talk about this. This is a classic Regents question. Which of the following particles will, go through X but be stopped by Y? So let's just look. Look at alpha. Alpha is blocked by the hand. So alpha can be stopped by your hand or a sheet of paper. Look at this. Beta can go through your hand but is stopped by aluminum. If you can't read it, it says beta passes through skin but not aluminum or wood. Now this is actually not completely accurate. Beep, beep, beep. So look what happens. Gamma, like I said, gamma's coming to get you. Gamma can only be partially stopped by thick slabs of lead or concrete. So gamma radiation, it's coming. Now, we can do things to slow it down, but we cannot prevent it from coming through. Have not seen any gamma decay equations on the Regents. Not to say that they don't exist, just not in the Regents. The last kind of decay equation is called positron. So if you want to take a look on table O, positron is very similar to beta, except for the charge. This is actually part of the antimatter spectrum. Gee, I have so many questions about antimatter. Can you share them with me, Mrs. Medica? No, I can't. That is a physics question for Mr. Andrews. Find him, ask him. All I know is that positrons are anti-electrons. No mass. Well, technically the mass of an electron is 1 over 1836 AMU, which the Regents calls 0. So no significant mass. Charge of +1. All right, how do we do a positron decay? Neon 19. If I didn't tell you it was positron, you go to table N, neon 19, about halfway down the page, it's a positron. So what's going to happen? Let's write a positron symbol. 0 over positive 1. B with the tail. Okay, what happens? Follow law of conservation. 19 is here. 0 plus 19. 10 protons here. How am I going to get a total of 10 protons? 9 plus 10. Okay, who is number 9? I got to look on periodic table. It's not going to be neon because we've transmutated naturally. This is fluorine. You can say plus energy if you'd like. So before we go to the next part, what happened? Mass didn't change. Protons down by 1. And so if mass didn't change and protons went down by 1, what happens to neutrons? Oh, I think I heard you in the back. They increase by 1. One last one. So calcium 37, if I didn't know it was positron, I take a look at table N. Calcium 37, third one from the top, it's positron. 0 over positive 1e. Oh, wait, you can write it like that? Yes, you can. Check table O. It shows you that positron is 0 over plus 1e or 0 over plus 1b with the tail. Okay, who's it going to transmutate into naturally? Total mass 37. Nothing's going to change here when it spits it out. 37. Total protons 20. 1 plus blank has to give me 20. 19. Total mass conserved. Who is number 19? I got to look it up. It's potassium. All right, and you can say plus energy if you want. All right, that's it. Good work today, guys. Hope this helps. If you have any questions, please email me or Mrs. Davis, post on Classroom, ask each other, help each other, and hold on. Let's have some music to go out on. Radioactive, radioactive.